Good morning everyone, I am Mr. Ish. Thank you for joining me. In this video we're looking here at a specific differential equation application which relates to a real life phenomenon, a biological phenomenon. The change in concentration or change in time for something. What is that something? We're looking here at glucose intravenously administered into a human. As soon as that glucose is administered at a constant rate, the minute it enters the bloodstream, the glucose levels begin to decline with time because of metabolism or excretion or entry into other cells. That glucose concentration rapidly decreases over time. This differential equation talks about that specific phenomenon. Our task in this is several-fold. We will do some limit evaluations at the end, but we have to solve this differential equation. We want to specifically determine the equation which will address the concentration of that glucose over time. Given this specific value over here, that at time 0 the concentration of glucose is equal to CO, that C subscript O means that the initial concentration of glucose is exactly what you're looking at. At time 0 you're only measuring or able to measure the initial concentration of glucose. How can we solve this with regards to that? There are two ways of solving this differential equation. You can do this in terms of the linear style, or you can do this in terms of separation of variables. The separation of variables is the harder way and the longer way, but we will do them both for the specific purpose of practice. When you're looking at this derivative factor dc or dt, that c and t represents our variables. Everything else that you see, r and k, are constants. This c is the same thing as that c, so you have to keep that in mind. When you want to do this by separation of variables, take that entire item onto this side. You'll have 1 over r minus kc. We can keep this as a capital C times dc or dt is equal to 1. That's exactly how you'll start this separation of variables procedure. Now you're going to do the integral over here. Bring in the integral. Everything here with regards to dt, because the variables are c for concentration of glucose in the bloodstream, and t for time. When you're looking at this, you can do a u substitution. If u is equal to r minus kc, then du is equal to minus k dc, and dc is equal to du divided by minus k. Remember, separation of variables is one way. The linear style using the integration factor is another way. That's the easier way. This is the harder way. We're doing them both. You have minus 1 over k integral 1 over u du is equal to the integral dt. When you're doing this, you're having minus 1 over k natural log u. From here you're having a t plus c, and I'm putting a 1 over here to distinguish it from this c. This is the constant of integration. That's my variable which implies concentration of glucose. Take the k on the other side with the minus sign. Natural log u is equal to minus k parentheses t plus c1. Take the natural log on the other side and resubstitute the u. The u was equal to r minus kc is equal to natural log on the other side, bringing the exponential minus kt minus kc1. You see how I've opened it up? There's nothing wrong with opening it up. Absolute value on the other side, r minus kc is equal to plus and minus e to the power of minus kt minus kc1. I'm only focusing here on the positive value. The negative value can go out. Bring the laws of exponents over here and I'll show you exactly what I'm talking about. R minus kc is equal to e to the power of minus kt times e to the power of minus kc1. You see, when you multiply these, the bases are the same, the exponents add, you get that. A substitution is needed here. A is equal to e to the power of minus kc. This will substitute for this right here. R minus kc is equal to a e to the power of minus kt. Now start solving for this c, because in the end we have to develop this expression here for concentration with regards to time. Minus kc is equal to a e to the power of minus kt minus r. Kc is equal to, flip these around by means of the negative, r minus a e to the power of minus kt. C is equal to r over k minus a over k e to the minus kt. You can bring this all under a common denominator if you want, but we still have to do this part right here. At time 0 we have a initial concentration of C0. At time 0 we'll have this value, r over k, and we're putting 0 here in place of t. We'll have minus a e to the power of 0 over k. E to the power of 0 is just a 1. We'll have CO, initial concentration, is equal to r minus a over k, and you're solving for that a because we'll do a substitution. A is equal to, or let's just say minus a is equal to COK minus R, and then A is equal to R minus initial concentration K. this value right here will come right over here. And let's bring it in. C is equal to R over K minus R minus initial concentration times K over K e to the power minus KT. This is my end result here from your separation of variables technique, which I want to put for you right over here, because it will have to be reconciled. It will look a little different from the one you will obtain from the linear style of solving differential equations, but it's still exactly the same, and we'll reconcile it. And this now can be presented here in a good way, because we've brought in the CO and all of that. This right here will be now your concentration with respect to time is equal to all of this, R over K minus R minus initial concentration times K over K, and then e to the power minus KT. This is my end result here in terms of the concentration with respect to time for this differential equation solved by means of separation of variables and utilizing this specific fact here that at time 0 your concentration is equal to C subscript 0, which means initial concentration. Of course, at time 0, as the glucose is being intravenously administered, your concentration when measured for that glucose will be equal to your initial concentration of that glucose. The linear style is very easy approach. dC over dt plus kc is equal to r. I took this on the other side. Now look what it looks like. It looks like dy over dx plus py is equal to q. It looks like that. Everything is already in the good format. You have to do your integration factor. That's always e integral p dx. So here we're having e integral. What's my p value here? It's k. And now we're not going to be doing dx. That's just our standard equation format. We're doing dt because everything here is with respect to time. When you're doing the e exponent integral k dt, you're getting e kt. This right here is going to multiply with all of that. E exponent kt will multiply with your linear style differential equation, and you'll open it up and you'll get all of this, which you should be familiar with now. E to the kt kc is equal to e to the kt and then r. You have to look at the factor which gave you this by means of implicit differentiation, d over dt. You'll always look at this and you'll always look at that and combine them. C e to the power of kt is equal to r e to the kt. Integrate all of this. I'm going to integrate right after the constant. When you integrate this, these things cancel out, but you'll just have a c e to the power of kt is equal to, when you integrate this, you'll have r e to the power of kt over k plus c1. You have to solve for c. C is equal to, you take this e to the exponent kt on the other side, it'll cancel out with that, but attached to that you'll have r over k, it'll cancel out with this, plus c1 over e to the kt, which you can rewrite again with this, everything brought up here along the numerator, c1 e to the power of minus kt. Now this right here is everything prior to us looking at this part. Now you have to bring that part into the picture. You'll have the initial concentration is equal to r over k plus c1 e to the power of minus k times 0, because value here is 0, variable 0. You'll have e to the power of 0, which is really nothing. You're just solving for c1 now. c1 is equal to co minus r over k. This can now right here substitute for this right here in this part, and you'll get your final equation. Concentration with respect to time is equal to r over k plus initial concentration minus r over k. This is being substituted for the constant of integration, e to the power of minus kt. This is what I'm getting by means of the linear style of solving for differential equation, which is really equivalent to exactly what you see over here, and I'm going to show you why it is. This is the end result from the linear style of integrating factor method. This right here is the end result from the separation of variables style, but they're equivalent, and right over here I'll show you that to be the case. You don't need to see any of this other stuff anymore, you know it. Open this up right over here. When you open this up, you're getting concentration with respect to time is equal to r over k. Hit the minus with everything you see over here. You'll have a plus. You'll have a initial concentration times k minus r over k e to the power of minus kt. Separate these out into their individual denominators. This is equal to r over k plus cok over k minus r over k e to the power of minus kt. This k and that k cancel out. You'll have r over k plus initial concentration minus r over k e to the power of minus kt. Concentration with respect to time, it's equal to that. Now if you compare this with this, they're exactly the same. So the end result from the separation of variables technique and the end result from the linear style of solving are exactly the same, and that should be the case. If you use two different approaches, the end result should be the same unless you use different means of simplification, but they can all be reconciled at the end. And now, we've shown you the case that the equation is exactly what you see. Let's complete this question now by means of the two limits we have to look at. The whole purpose of this entire exercise, separation of variables with the linear style, is to arrive at this equation, which can now give you the concentration of glucose in your blood at any time after it has been administered. We have to find limit, or what does this function approach in terms of limit as time approaches 0. What does this 0 mean? It means at the initial time. We're looking here with regards to concentration function, which is right here, your concentration function. What will this function approach right at your initial start? Think about it. What will you do over here? You can literally put 0 here in place of t and solve and see what happens. When you do that, you have r over k plus you'll have co minus r over k times e to the power of 0, which is just a 1. You can open this up. You'll have r over k plus co minus r over k. These will cancel out and you'll have CO, and that's exactly a very good answer because it's confirming you right here, this specific part. At initial time, t equals 0, minutes, seconds, whatever it might be, your concentration at that time of the glucose in the bloodstream should equal obviously your initial concentration, and it does, and it makes sense and it's right. The second and the last limit we want to evaluate is what happens as time t approaches infinity. After that glucose has been administered to your blood, what does your function approach in terms of this limit as t approaches infinity? An indefinite time later, where has that glucose ended up? What is the value of your glucose concentration in the blood by means of this function? Well, you can literally put infinity here in places of t. You'll have r over k plus co minus r over k e to the power of minus infinity. Minus kt, infinity coming in here. K is meaningless in the face of infinity. This is no different than you looking at everything here, 1 over e to the power of infinity. 1, anything divided by an extremely large number zeros out. This right here is no different than you multiplying it by 0. All of this will zero out. The only thing which will remain is this. So your answer will be this, and it should be right, because as the time approaches infinity, that glucose concentration has been eliminated from your blood by metabolism, secretion, excretion, or whatever it might be, input into the cells. The only thing which remains is your r over k value from the function. At time t approaching infinity, your function will always approach this value here, r over k, and it'll be a constant value. And that right here is basically the end result of this entire process of differential equation application. And with that, I thank you for watching this video. Have a good day.